Hello, how are you? This lesson is from textbook Larson Calculus 11th edition, chapter 13.5 regarding chain rules. First, I'm going to take a few minutes of the time. I'm going to discuss the derivative of a composite function from calculus 1 for a single variable. If you recalled, the definition of a derivative was f prime of x was the limit as delta x approaches 0 of f of x plus delta x minus f of x over x over delta x. That was the definition of the derivative for a single variable. Also, we had an alternative form. If we had a continuous function at the point C, and in this neighborhood of point C, for every one of these x value, we did have a y value. Therefore, I can pick a arbitrary point either to the right or the left, such as, and call it point X, and the y value is f of x, and this one is c and f of c. Therefore, instead of writing it as the change in the 2 points to represent it by the delta x, the change between these two is going to become x minus a c. Therefore, this is called alternative form of a definition of the derivative as a point at a point. This is at any point, this is at a specific point, is equal to the limit as x approaches point C of f of x minus f of c over x minus c. This is something we need to know because we're going to use this one to prove the chain rules. And what do we have to know the chain rules? Chain rule is going to be applied when we have composite function. Let's talk about a composite function. I'm sure you have been to many restaurants, and then such as Burger King, and then you see somebody is cooking the hamburger patty here, and this one is a raw hamburger patty. You have a cooked one, then somebody gonna pick this one up and use a bun and put the hamburger patty, put in that one, and shift it to here, and somebody gonna put mayonnaise and lettuce, and then eventually through a chain, the hamburger is gonna be ready. This is nothing except called a chain rule. And these are linked together. If one of these links get interrupted, therefore you do not have any output. In mathematics, I'm going to give you an example. If you have f of x equal to sine of x, that x is an arc length, and it can be any real numbers. And then I'm going to write f algebraic function such as x squared plus 3x, and this one x can take any real numbers. If I go ahead and replace that x, which is a placeholder, with the function g of x right here, this is called a composite function. Therefore, I have to go back and replace that x with this one right here. Means the input of this link is the output of the first link, and that's called the sine of x squared plus 3x. And how do we take the derivative of these function? Because it's a composite function, and because this is a function inside another function. This is what we need to know about the chain rules. Okay, let's talk about the chain rules. I'm going to take the limit as x approaches c. Therefore, I have that function f of g of x. This is f of g of x minus f of g of c, and in this one I'm going to write this one as x minus c. Therefore, whenever I applied that rules, I have to be able to use some mathematical calculation to be able to find the derivative of that chain rules. what I'm going to do right here, I'm going to multiply here top and the bottom by same quantity, which means 1. And I'm going to do this one as g of x minus g of c over g of x minus g of c. This is nothing except a multiplied by 1. Therefore, this quantity has not been changed. And I'm going to go ahead and rewrite this one. I'm going to put this g of x minus g of c over x of c over x minus c, and this one over that one. Therefore, I'm going to write f of g of x minus f of g of c over g of x minus g of c. This is nothing except just like that one. When we had x plus delta x minus x, you become a dx. In here, I have g of x minus g of c instead of x plus delta x and x. Therefore, when I subtract this one right here, it becomes this one. And this is nothing except if I take the limit as x approaches c, this is nothing except the derivative of that function is outside function with the difference of the distances which are the inside. Therefore, this is f prime while the g stay the same. And if I write g of x minus g of c over x minus c, this is nothing except the derivative of the inside function, and this one I can write, and this one, remember, this is the limit of the product. You have to write as the product of two limit. You can write a limit over here as x approaches c, and that would become g prime of c. I'm sorry, here that should become a c because I'm getting it at the point c. Therefore, the derivative of f of g of x is the derivative of the outside function with the inside function stay intact times the derivative of the inside function. That is what we learned in Calculus 1. But my question is today, what happens if we move on to multivariable calculus? And in multivariable calculus, we have f of x, y equal to maybe x squared, y squared plus 3x minus a 5y. And remember, f of xy is nothing except a different way of writing a variable z. The same way, instead of a y, we wrote f of x as long as we use x to describe the function. Therefore, in here, as long as we use x and y to describe the function, therefore, we know the output of this one is function z, is the variable z. How do we take the derivative of that one? As we discussed in 13-4, this one, you cannot take the derivative of it like derivative of z respect to x. Why? Because in here you have two independent variable. Then if you do it with respect to x, what you're going to do with respect to y. Therefore, we discussed in chapter 13.4 that in here we cannot take the ordinary derivative. We have to take partial derivative of z respect to x, and we did prove it as long as you keep the y constant, and that would become 2x times y squared plus 3. Derivative of x respect to x is 1, and derivative of y is a constant, and that would become a 0. And what is the partial derivative of z respect to y? This is become 2y, but x squared is a constant. Derivative of 3x is a constant, is 0, and derivative of the negative 5y respect to y is negative 5. Okay. We don't have any issue at this moment. Therefore, we do have a function z. The function z uses two independent variable, x and a y, but these I have to use partial derivative since you have two independent variable. But there is if what happened if that x itself is depend on another variable? Like what happened if that x represented by t squared plus 3t? Then when you take the partial derivative of the z respect to x, that would become the outside function because x is a function of t, and this is your inside function because you have to replace the x with t squared plus 3t. And what happens if the y is also a function of t? Therefore, you have to replace y with the 1/2 t. Therefore, this one also is a function. Therefore, in order to get from a t to z, you have two routes. That's one route, that's another route. Therefore, what is the derivative of z respect to t? You might ask that why did you use ordinary notation for the derivative? Because x and y are function of single variable. If x and y were function of multivariable, then I couldn't use ordinary. And I'm going to talk about it in a few minutes. I have to use the partial. Therefore, in order to get to here, you have two routes. Therefore, you have to give me the rate of change of what? Rate of change of z respect to x and t respect to x respect to t. Therefore, in here is going to become partial derivative of an outside function times the derivative of inside function plus, because you're going to have two different routes, partial derivative of z respect to a y times the derivative of y respect to a t. Therefore, this will represent the chain rules. Okay, another student gonna say, well, there are many different occasions because we are in multivariable calculus when z is the function, if z is a function of x and a y, what happens if x itself become function of t and a s? What happens if the y become function of t and a s? Therefore, if your z is a function of x and a y, and x is a function of t and a s, and y is a function of t and a s, in order to get to the z, from t you have one route through x, you have one route through y. Therefore, you have to ignore the s because you have to take the derivative of z respect to t. But because x is also depend on a multivariable, here you cannot put ordinary derivative because you have to keep the s constant. Here you have to say partial derivative of x respect to t. In here you have to write partial derivative of z respect to x, partial derivative of z respect to y, partial derivative of y respect to s, partial derivative of y respect to t. Therefore, if I want to go from t to a z and say what is the partial derivative of z respect to a t, you have to take the derivative of outside function because this is your inside. You started from here. You have to take the derivative of outside function respect to x times the derivative of the inside function respect to t. And see, that becomes dz dt. But there are two paths toward the z from t. There is also another path from the y direction. Therefore, partial derivative of z respect to y times partial derivative of y respect to t. But how does z changes respect to s. Here you have no other option to make your t constant and write partial derivative of z respect to x times partial derivative of x respect to s. And what is left is dz ds plus partial derivative of z respect to y times partial derivative of y respect to s. Therefore, you always have to remember when your variable branches off to more than one variable, you always have to use partial derivative by holding the other variables, it could be 1 or 2 or 3, constant. And that's how you take the derivative of the multivariable calculus when you have a chain rules. Okay, let's do an example. The students, maybe we have a z and this z become x squared y. Therefore, your z is a function of x and a y. But the x is a function of t alone, and that make it t squared plus 1. And the y is a function of t alone and is a function of 3t. Many of you are going to say, well, that's the simple multivariable function. This is a simple parametric functions. What I'm going to do, I'm going to go write the z as a function of t, not as a function of x and a y. And instead of x squared, I'm going to write t squared plus 1 squared times y, which is 3t. And I'm going to simplify that one. And whenever I simplify it, that becomes 3t to the power of 5 plus 6t cubed plus 3t. Then I'm going to take, that's a single variable, taking the derivative of z respect to t, that's the ordinary, it becomes 15t to the power of 4 plus 18t squared plus 3. Perfectly fine. That's nothing wrong with that. But another student said, can I go ahead and branch off this one to x squared and y? Then for this is a function of t and that's the function of t, and write dz dt equal to partial derivative of z respect to x, which is 2x, and y is constant, times partial derivative of x respect to t, which is 2t, plus partial derivative of z respect to y, which is x squared, times partial derivative of y respect to t, which is 3. And come back right here and replace the x and a y with the t squared plus 1 times 3t times 2t plus t squared plus 1 squared times 3. If I simplify that one, that becomes t cubed, t to the power of 4. That's 2 times 3 is 6. 6 times 3 is 12. But don't forget, I have a 2 here. 2 times 3t is 6t times 2t is 12t squared. And when I do that one, that becomes t to the power of 4 plus 2t squared plus 1 times 3. And that becomes 12 and 3, it becomes 15t to the power of 4. There is a 12 in here, and there is a 6 in here. Let's make it 18t squared plus a 3. I think these answers are exactly the same. Would you go this route or this route? This is a self-judgment you got to make. Not all the problem is as easy as this one that you can choose that route. Sometimes these problems are so complicated that going this route is much easier than doing that route. Therefore, if I write z equal to x cubed y plus 3x minus 5y squared, and write my x to become function of t and a s, and that become s times t, and my y become function of t and a s, and that becomes square plus t squared. Well, either route would be easy, but I like to write it as branch of the z to the x and a y. And remember, z is coming to become x cubed y plus 3x minus 5y squared. But in here, you have to take the partial with respect to x. Therefore, the y is constant. And in here, instead of a y, I'm going to write x cubed y plus 3x minus 5y squared. That's partial derivative of z respect to y and partial derivative of z respect to x. Then this is nothing except, remember, I'm taking the derivative of that function. That's supposed to be your whole x. But here I have s and a t, s and a t. Let me scratch this one off and just write x to simplify it and just write t. Then if I want to know what is, here I cannot put ordinary function dz ds, because in order to go from s to a z, you have a route in the x direction, a route in a y direction, but also you can get to the z from t. Because you have two different routes in here, these are multivariables, you cannot use ordinary. You have to use partial derivative of z respect to s, which is equal to partial derivative of z respect to x times partial derivative of x respect to s plus partial derivative of z respect to y times partial derivative of y respect to s. This one respect to x is 3x squared y. Derivative of 3x respect to x is 3. And I hope you know the 5y squared is constant. When I take the partial with respect to x, that's become a 0. And I gotta multiply by the derivative of x respect to s, because t is a constant, that become only a t. Plus, what is the partial derivative of z respect to y? Therefore, this one become x cubed. This is constant, 0, negative 10y. Then I need a partial derivative of y respect to s. This is a constant, is 0, and that become a 2s. Because your x and y both are function of t and a s, your z at the end has to be a function of t and a s. Therefore, I go right here and replace the x with st, the y with t squared plus t squared, and a t, plus x cubed is st cubed minus 10 quantity squared plus t squared times 2s. The student is going to say, oh, it's so difficult to combine all of these and simplify it. It is not necessarily to simplify your derivative, because eventually they're gonna ask you how fast your z is changes at the point of s equal to the t equal to 1 and s equal to 2. Then by plugging those numbers in here at the very end is a lot easier to simplify. Therefore, that was the short lesson regarding the chain rules in multivariable functions. Thank you, and I hope to see you in next video.